AI broke the internet again, and this week has been absolutely insane. Mistral releases a model that now completely saturates the mini F2F math benchmark at 100%, solves 587 out of 672 Putnam competition problems, and automatically found 5 previously unknown bugs in open source code bases. Tencent officially releases Hy3, their 295 billion parameter open source model rebuilt from scratch in under 90 days, with competitive scores on SWE Bench Verified and BrowseComp, and pricing at just $0.063 per million input tokens. Intern Science drops Agents A1, a 35 billion parameter agentic model that's setting overall state-of-the-art on both the Seal Zero Long Horizon Search benchmark and Frontier Science Research. Bytedance releases a new visual geometry model that beats the previous best by 35% on camera pose accuracy and 23% on geometric accuracy. And it was just accepted as an oral paper at ICLR 2026. We have a new open source text-to-image foundation model built with a completely new architecture that puts semantic structure ahead of texture generation. And researchers release GenRecon, a new tool that takes just 8 photos of a room and reconstructs a complete, editable, high-quality 3D scene that beats every other reconstruction method by 16% and a lot more. So let's jump right in. First up, Mistral releases a pretty extraordinary new model this week. It's called Leanstral 1.5, and this is a formal reasoning model built for proof engineering in Lean 4. And the results it's posting are genuinely impressive. Now for the benchmark numbers. Leanstral 1.5 completely saturates mini F2F, reaching 100% on both the validation and test sets. That's not 99%. That's perfect coverage of the entire benchmark. On Putnam Bench, which has 672 problems from the Putnam Mathematical Competition, one of the hardest undergraduate math contests in the world, it solves 587 of them, edging out the previous top result from Seed Prover 1.5 by 7 problems. On Fate H, which tests graduate-level abstract algebra, it hits 87%, a new state-of-the-art. And on Fate X, which is PhD-level problems in areas like group theory and ring theory, it scores 34%, also a new state-of-the-art. Now the really interesting number is the cost comparison. Seed Prover 1.5's high setting runs on a budget of 10 H20 days per problem, which the team estimates at $300 or more per problem solved. Leanstral 1.5 costs roughly $4 per problem. That's a 75 times lower cost for a higher result. And this model also shows the strongest test time scaling behavior the team has ever seen in a formal reasoning model. As you raise the token budget per attempt from 25,000 tokens all the way to 4 million, performance climbs smoothly and consistently the entire way. At 50,000 tokens, it solves 44 Putnam problems. At 200,000, it solves 244. At 1 million, it solves 493. And at 4 million, it solves 587. In other words, you can just throw more compute at it, and it keeps getting better in a predictable, linear way. Beyond math benchmarks, they also ran it on real open source software repositories. Using an automated pipeline where the model generates correctness properties from actual Rust code and then tries to prove them formally, it flagged 47 violated properties across 57 tested repos, with 11 pointing to genuine bugs. 5 of those bugs were previously unknown and unreported on GitHub. One example is a sign function in a zigzag decoding library, where a specific input value caused an integer overflow that would crash in debug mode and silently corrupt data in release mode, the kind of edge case that testing and fuzzing typically miss. For your reference, it also surpasses Claude Opus 4.6 on FLT eval, which is a benchmark of real pull requests from the Fermat's last theorem repository, at 1/7 of the cost. Now, architecture. Leanstral 1.5 has 119 billion total parameters, but only 6 billion are active at inference time. The model goes through a 3-stage training process: mid-training on formal mathematics and code, supervised fine-tuning, and then reinforcement learning using a custom RL algorithm called CISPO. It operates in 2 RL environments: a multi-turn prover, where it submits proofs and iterates on lean compiler feedback, and a code agent environment, where it edits files, runs bash commands, and uses the Lean language server in real time like an actual developer. Now, can you run this on a consumer GPU? With 6 billion active parameters, this is actually quite lean for inference. You'd need a GPU with enough VRM to load a 119 billion parameter Mo checkpoint, which in practice means this is best suited to server-grade hardware or cloud inference. The awesome thing is, they've released this already under Apache 2.0. The weights are on Hugging Face, and it's also available as a free API endpoint. You can use it right now through Mistral Vibe. If you're interested in reading further, I'll link to this page in the description below. Also this week, Tencent officially releases a pretty impressive open source model. It's called Hy3, and this is the full official release of Tencent's Hunyuan 3 model, following the preview they released back in April. Now, for context, Tencent tore down their entire pre-training and reinforcement learning infrastructure back in February 2026 and rebuilt everything from scratch. They started training Hy3 6 weeks after that. The full official version is now out, with further gains in coding and agent capabilities over the preview. For your reference, here are the key specs. Hy3 has 295 billion total parameters, with 21 billion active parameters per forward pass, a 256,000 context window, and a 3.8 billion parameter multi-token prediction layer. It supports 3 configurable reasoning modes: no-think for fast direct responses, low for light reasoning, and high for deep chain of thought, which you can set per request. On benchmarks, the official version scores 74.4% on SWE Bench Verified for coding agents. That's behind Claude Opus 4.6 at 80.8% and GPT 5.4 at 78.6%. But it's genuinely competitive for an open source model at this active parameter size. On BrowseComp and Wide Search for search agent tasks, it posts competitive results against other open source models. Now, the production numbers are actually what I find most impressive. When Tencent deployed the preview version into CodeBuddy and WorkBuddy, they measured time to first token dropping by 54%, end-to-end response time dropping by 47%, and a success rate of over 99.99%. Now let's talk about pricing. On Tencent Cloud, Hy3 is priced at 1 yuan per million input tokens and 4 yuan per million output tokens, which works out to roughly 14 cents and 55 cents at current rates. On OpenRouter, through third-party providers, you can access it for as low as 63 cents per million input tokens. Now, can you run this on a consumer GPU? At 295 billion total parameters, it's not going to run on a single consumer card. You'd need a serious multi-GPU setup, or to use it through a cloud API. The weights are on Hugging Face, and it supports both VLL, M, and SGLang deployment. The awesome thing is, they've released this already under Apache 2.0. You can download it right now and deploy it with an OpenAI-compatible API endpoint. If you're interested in reading further, I'll link to this page in the description below. Next up, we have a really impressive new open-source agentic model. It's called Agents A1, and this is a 35 billion mixture of experts model from Intern Science that's built specifically for long-horizon agentic tasks. Now, for the benchmark numbers. On Seal 0, which tests long-horizon search and is one of the hardest agentic benchmarks out there, Agents A1 scores 56.36, which is the overall state-of-the-art result on that benchmark right now. On BrowseComp, it scores 75.51, which is the best result among comparable 35 billion class models. On SciCode for engineering tasks, it scores 44.33. On Frontier Science Research for scientific reasoning, it scores 40.0, which is also the overall state-of-the-art on that specific benchmark. And on IFbench for instruction following, it scores 80.61, another state-of-the-art result.
The training approach is interesting. They use what they call a domain-grounded knowledge action graph, which turns agent process traces into trainable targets. Training goes through 3 stages: full domain supervised fine-tuning to align broad agentic behaviors, domain-level teacher models that capture specialized expertise for each area, and then multi-teacher on-policy distillation to transfer that expertise efficiently into the final model. In terms of deployment, it runs through standard VLLM or SGLang with an OpenAI-compatible endpoint and supports the full 256,000 context length. Now, can you run this on a consumer GPU? A 35 billion MOE model is actually much lighter to serve than a 35 billion dense model. So with the right quantization and a high VRAM consumer GPU, like an RTX 4090, you could potentially serve this at reduced precision. The awesome thing is they've released this already on Hugging Face with the weights, code, and an open evaluation framework for reproducible benchmarking. If you're interested in reading further, I'll link to this page in the description below. Also this week, we have a pretty fascinating new open source image model. It's called SeFI Image. And this is a text-to-image foundation model built with a completely new approach called semantic first diffusion, which changes the fundamental order in which images are generated. Now you see, the problem with standard diffusion models is that they denoise both high-level structure and low-level texture at the same time, which means the model is simultaneously trying to figure out what an image should look like and how it should look in the same process steps. SeFI Image separates these into 2 streams. A semantic stream handles the high-level structure, things like object placement and composition, and a texture stream handles fine-grained details. But crucially, the semantic stream denoises first by a small time step offset. So by the time the texture stream runs, it already has a clean structural anchor to follow, instead of figuring out both from scratch. Now for the benchmark numbers. On GenEval for object following and compositional reasoning, the 5 billion parameter version scores 0.88. putting it above Flux2 Klein 9b at 0.85 and Z-Image at 0.84, and just behind Quen Image at 0.87. On Long Text Bench, for rendering long Chinese and English text and images, it scores 0.978, which is the top result on that benchmark, ahead of Joy AI Image and Quen Image. And on 1IGEN, for omnidimensional instruction generation, it scores 0.5606, again, the top result. On DPG Bench, for detailed prompt following, it scores 87.27, placing it just behind Quen Image and Z-Image. Now for compute. The 5 billion model was trained with 125,000 A800 GPU hours total. The model comes in 3 sizes: 1B, 2B, and 5B. The 1B and 2B versions are absolutely runnable on a consumer GPU. The 5B would need around 10 to 16 gigabytes of VRAM, depending on quantization. The awesome thing is they've released all 3 model sizes already. Weights are on Hugging Face, the code is on GitHub, and the paper is on Archive. If you're interested in reading further, I'll link to this page in the description below. Next up,
Bytedance releases a really impressive new 3D geometry model. It's called DepthAnything 3, and this can predict spatially consistent geometry from any number of visual inputs, with or without known camera poses. And the benchmark numbers here are actually pretty wild. On their new visual geometry benchmark, covering camera pose estimation, any view geometry, and visual rendering, DepthAnything 3 surpasses the previous state-of-the-art method, VGGT, by an average of 35.7% in camera pose accuracy and 23.6% in geometric accuracy. That's a genuinely large jump. And it also outperforms its predecessor DepthAnything 2 on monocular depth estimation, despite not being specifically designed as a monocular model. Now, what's genuinely interesting about the approach is the design philosophy. They used a single plane transformer, specifically a vanilla Dino V2 encoder with no architectural specialization at all, and a singular depth ray prediction target, which avoids complex multitask learning. The claim is that you don't need a fancy, purpose-built architecture to achieve this level of geometric understanding. Now, how this works is the model uses a depth ray representation, meaning each pixel's depth is represented as a ray in 3D space, rather than just a scalar value. This makes the geometry prediction inherently multi-view consistent across any number of input images. Here are some examples. You can see it recovering the full 3D geometry from a difficult video sequence, building a large-scale SLAM map that stays more accurate than ColMap with none of the 48-hour processing time, and outputting 3D Gaussian splat parameters directly for novel view synthesis from just a frozen backbone plus a small DPT head. The community adoption for this one is actually already really impressive. There are already integrations with Blender, Comfy UI, ROS2, and a web XRVR viewer, all built by the community after the code released. Now, it was accepted as an oral paper at ICLR 2026, which is one of the most selective designations in machine learning research. All models were trained exclusively on public academic datasets, and the paper is from Bytedance Seed and a group of university collaborators. Now, can you run this on a consumer GPU? Yes. The Dino V2 based backbone is well studied and can run on most modern GPUs. The exact VRM requirements depend on model size, but the community Comfy UI integration suggests consumer hardware is fully supported. The awesome thing is, the code is already on GitHub, and a live Hugging Face demo is available right now. If you're interested in reading further, I'll link to this page in the description below. And finally this week, we have a pretty cool new open source 3D reconstruction tool. It's called GenRecon, and this can take just 8 photos of an indoor room and reconstruct a complete, high-fidelity, physically based 3D mesh with full material properties that you can then import directly into standard rendering pipelines like Blender or Unreal. Now, you see, the problem with most 3D reconstruction methods right now is that they fail in 2 very specific ways. First, they produce noisy or over-smooth surfaces in challenging areas like curved furniture, fine objects, or complex materials. And second, they just leave occluded areas completely blank, the parts of the room the camera never directly saw. GenRecon solves both of these by doing something genuinely different. Instead of treating reconstruction as a pure geometry estimation problem, it frames it as conditional 3D generation. So how this works is the scene is partitioned into overlapping 3D chunks that tile the entire space. Then, a projection-based conditioning mechanism lifts the posed image features from all your input views into a coherent 3D representation that's view order independent and spatially anchored to the scene. All the chunks are then generated jointly in a shared latent space, enforcing consistency across the boundaries. The key ingredient is Trellis.2, which is one of the best object-level generative 3D models out there, scaled up to work at full scene level. So the generative prior isn't just for filling in gaps. It's responsible for the overall quality of the entire reconstruction. For your reference, GenRecon outperforms all cutting-edge reconstruction baselines by 16% in geometric accuracy on their benchmark. And in the side-by-side comparisons on their project page, you can clearly see that areas which other methods leave blank or noisy, GenRecon produces complete, clean, material-accurate geometry. The output mesh has full PBR materials, meaning you can relight and edit it in any standard rendering pipeline, and it will respond realistically to lighting changes. The awesome thing is they've released the code and checkpoints already on GitHub. Code dropped June 29th, just a few days ago. This is from researchers at TU Munich, including Matthias Niesner's group, and co-authors at ETH Zurich. If you're interested in reading further, I'll link to this page in the description below.